Hello, everybody. This is Mr. Folly, and welcome to, welcome to 10.2, where we're going to talk a little bit about Le Chatelier's principle and shifting equilibrium. All right. So starting off, when a system is at equilibrium and a stress is applied to the system, a stress, oh goodness, a stress, okay? It's applied to a system, the reaction shifts to relieve that stress. I wish it was that easy for all of us. Here's a stress. No, let me shift. I have no stress anymore. All right, but that's what happens with equilibrium systems, and we kind of do that too. This is based on the collision theory and needs to be explained using collisions, successful collisions compared to the opposite direction. Okay, so our stresses are going to be talking about collisions, successful collisions compared to the opposite direction. All right, so stresses. I can increase a concentration. So notice again, I'm going back to this reaction. Well, not back to, I guess I haven't used it yet. Here's a reaction, okay? So if I add something, if I add more A, there'll be more collisions on A's side. Adding more A means more A's will collide with B. So it will have more successful reactions per time than the opposite reaction. Notice again, more collisions and more successful collisions compared to the opposite reaction. So adding shifts away. AA is how I remember it. Adding shifts away. Adding shifts away. Adding more D has no effect, no effect, no effect, no effect, no effect, as solids and liquids do not change concentration, so rates don't change. So boo, 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 boo. No change for solids nor liquids. Okay. Decreasing concentration. Okay. It's going to shift towards it. Okay. So notice we're all the way down here. If I remove, it's going to shift to replace it. Side reactions are the cause for this. So look for a positive attracting a negative. Now, I don't have that in this example, but a positive would be attract to a negative. So substance C has a side reaction with your mom and remove some C from the system. If I remove C, it's gone, right? The reverse reaction, going from right to left, will have fewer collisions with C and D. So the reverse reaction will be slower than the forward. So this is going to shift towards the thing you lost. If I remove C, it will shift to the right-hand side to replace it. So let me just make that clear. Remove C shifts to the right-hand side, and it replaces the lost C. Okay? Increasing pressure. Now it says right away, increasing pressure shifts towards less gas. So the way you increase pressure is, if I'm in jail, of course I am, and I'm sitting in my jail cell, if you want to increase my pressure, you can make my jail cell be a little bit smaller. Oh no! Then they've done studies about the pressure of just the size that you have in jail. Don't go to jail. Be good people. All right. So increase in pressure will shift towards less gas. So that means if I have two people in here, let's say I have two people in here, and the room got this small, guess what? I'm not going back to jail again. I don't like being that close to people, right? I am antisocial, which is how I got in jail to begin with. Just kidding. I passed my background check. I was not in jail. All right. So increasing pressure is going to shift towards the side with less gas. Pressure only affects gases. The system with more gases will have more gases collide, react, and change to non-gases. The number of gases includes the coefficient. If the pressure increases, it shifts to the left-hand side to reduce gases. Why is that? Okay, so I'm going to look over here. I'm looking at my dude right here. And what I notice I have is on the left-hand side, I have one gas. And on the right-hand side, with the coefficients, right, I have three gases. So if I increase the pressure, it will shift to the side with less gas. That means in this case, it will shift to the left-hand side. So increasing the pressure will shift to the left-hand side to reduce the gases. That's the stress. It's too crowded. It's going to shift to have less crowdedness, less stress. Decreasing pressure shifts towards more gas. Hey, that's the opposite. That makes sense. Now, here's the thing that comes in here. The way you decrease pressure is by changing the volume. If you decrease the volume, I talked about this volume right here, you increase the pressure. And increasing the volume decreases the pressure. Increasing the pressure means more collisions, so it'll shift towards fewer gases. All right. Adding heat shifts away from the heat term. Okay? So you will often see a heat word just like this. If I see exothermic, which is very common, exothermic, heat on the right. And if I have delta H equals a negative number, then heat is going to be on the right-hand side. Okay, and the flip is true. Endothermic would be heat on the left-hand side. Positive delta H would be heat on the left-hand side. Okay, so adding shifts away, add away. Adding heat to the top one, if I add heat, it shifts away. That's going to be the left-hand side. Adding heat to the second one, it's going to shift away. That's going to shift to the right-hand side. Only changing temperature changes K's value. That's important. K never changes unless you change the temperature. K never changes unless you change the temperature. K never changes unless you change the temperature. Did you write that down? I know you did. When heat is involved, shifting right increases K. This is only for heat, only for heat, only for heat. Shifting right increases K, and shifting left decreases K. Okay, here we go. Examples. So let me have some fun here. Let's go to extra thick black. See if you're paying attention here. I know your answers are in here, but let's see if we can talk our way through each of these. Okay. Plus, I like to write in the yellow. It kind of makes my handwriting pop a little bit. Makes me feel special. Okay. So if I increase pressure, it will shift the reason to fewer moles of gas. So I have to figure out which side has fewer moles of gas. This side over here has 4. Oops, I'm going to go to red. I think I can actually see that. This side has 4, and this side has 2. So it's going to shift to the right-hand side because it has fewer moles of gas. Increase the temperature. It's going to shift away from heat. Delta H is negative 92. Well, if it's negative, that means plus heat on the right-hand side. So it's going to shift to the left-hand side. Increase in concentration of nitrogen and hydrogen. That's going to shift, adding shifts away, right-hand side. More collisions for N2 and H2 shift, right-hand side. Increased concentration of ammonia. There's ammonia. Adding shifts away. Oh, yeah. Adding's going to shift away. So it's going to shift to the left-hand side. And why? More NH3 collisions. Okay? Now, my reasons on here, I just want to point out, my reasons on here that are written underneath here, these are poor. Okay? The answers that I wrote in red and yellow are wonderful. All right, here we go. Let's do it again. Oh, extra thick. Let's play along with me, okay? Here we go. Oop, I got to make it back to my fine chisel. I am a fine chisel, am I not? Increased pressure. That's going to shift towards the side with less gas. I'm going to go to a brighter color than that. Okay? Shift, so it's shift side with less gas. This side has 9 gases. This side has 10 gases. That's going to be the left-hand side. If I increase the temperature, delta H is negative 909. That means heat is a product. If I increase the temperature, it's going to adding shifts away. Left-hand side, away from heat. Increase the concentration of ammonia and oxygen. So it's going to shift to the right-hand side. More collisions on left-hand side. Increase the concentration of nitrogen monoxide and water. Increasing these, it's going to shift to the left-hand side. And that's going to be more collisions, thus more reactions for NO and H2O. All right, got the last tricky part here. Here we go. Both these reactions are going to be catalyzed first with iron, second with platinum. We don't even care about that. I'm gonna hit this with a. Okay, so here we go. Let me go B and let me make it a little bit bolder. If you add a very specific color, that will increase the color a lot and then increase some. If you add a color, that color increases. Boom. Let me highlight that in something you can read. If you add a color, that color increases. Okay? For example, adding CH3COOH gets more yellow, even though it shifts away. If I add this, it's going to shift to the right-hand side, but not so much that it's not more yellow than it was before if I add this. It will shift to the right-hand side, but I'm still going to have more yellow. So like my spending increase. I won the lottery. Woohoo! I won $700 million. My spending increases. My spending goes whoop, right? Or heck, my spending goes whoop straight up. And then, or my money goes whoop straight up, and then I'm going to spend more. But at the end of the weekend, I'm still going to have more than I started with, right? If I started with $20 and I end with 7 billion or whatever it was, I'm going to end up, somewhere around here, around 2 billion when I'm done. Okay. If you remove CH3COH, if I remove this, it will shift right. So if I'm shifting right, so red goes darker and yellow goes less. They're bad word choices. Forget it. You get the idea, right? If I add red, more red. And more yeller. Oh, I put yeller for real. I didn't mean to put really yeller. More yellow. But more red wins. If I add yeller, I get more yellow. And because I'm shifting to the right? I'm shifting to the right. I get more red too. But more yellow wins. So what happens? It gets yellower. So we know yellow and red make orange. So if it shifts left, it would be lighter orange. If it shifts right, that would be darker orange. And it shifts to be done with a podcast. Then you say, hey, we're done. To which I will say, toodles.